Hello class. So this will be the last video on section 1.1 where we're talking about direction fields. Just as a reminder, in the previous video, we went over an example of what information you can get from a direction field. In particular, we saw that given a differential equation of the form dy dx equals f of xy, by plotting a portion of the tangent line at each input xy, we can get this sort of picture that what does it do? Well, at each point, it tells you what the slope of the derivative, what the slope of the function should be, right? Because that's what the derivative is by definition, right? So we did a quick example, hand-drawn of what that looked like, and then I went and I showed you in Mathematica how you can draw a direction field that's more complete, right? So you don't have to be doing this for every point, x, y that you want to find what the derivative is, and also how to plot solutions in there, so you can see that the solutions do in fact follow the direction field. Then I show you another quick example where, so right here, where if you have y equals x squared, okay, and then, so I first drew the graph, then I just drew parts of the tangent lines, right? So each of those lines is just a portion of the tangent line, right? With the slope given as a derivative at each point. Then I erase the actual graph, and you see that the slopes of the tangent lines still give you a pretty accurate description of what the function looked like. And it's the same thing with differential equations. Even though you don't find what the actual solution is, you can just plot it, and you can have an idea of the general shape just by following the tangent lines that we plot in the direction field. So that's the idea. In this video, we're just going to do one more example of how this works. So here's an example of a direction field that corresponds to the differential equation dy dx equals x squared minus y squared. I got this example from the book by Sil. I think in a couple of videos, like I said, Sidro, the last name is actually Sil. So the author is Dennis Sil. It's a pretty good book. But anyways, this looks a lot like the direction field you get in Mathematica. The only thing is that here they put these arrows. You can put arrows if you want. You don't necessarily have to. I can show you how to do that in Mathematica. I'll probably have an option for that when I ask you to do it in the homework. But in general, this is pretty much the same thing you get in Mathematica. Right? This is the direction field given for this differential equation. Each arrow you look there is just a part of the tangent line, okay, to the graph at each point. So what we're going to do is we're going to use this direction field to graph solutions that go through each of these initial conditions, right? So we're going to do it in different colors. Let's say we start with A. I'm going to label this solution A. So we want to plot a solution that goes through the point -2, 1, right? The input is -2, the output is 1. So where is that? So x equals -2, y equals 1. Okay, that's about here. I want to plot it. Well, I can just follow the tangent lines. Okay? So it seems that it's increasing here. Here it goes a little bit straight, starts to go down, down, straight again, up, 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 up. And that's a general idea of what this solution is going to look like. Again, we don't know what the solution is. I don't know what this function is. But just by looking at this, I have a general idea of what the shape is. And we can also try it towards the left, right? It looks like it's going to be something like this. Oh, sorry. You don't want to do it vertical because that would not be a function. Okay. So it's as simple as that. Just find the point that is given, right? In this case, the point is x equals -2, y equals 1. Start with the point there and then just follow the lines. Okay. And as I mentioned, in a lot of applications, this might be all that you need to know about the function. You might not actually need to know what the actual function is. This might be enough. Okay. So let's say we do B here in blue. Actually, let's not use blue because it's blue there. So let's use purple. So we're given the point. So the input is 3 and the output is 0. So the point 3, 0. So x equals 3, y equals 0. Okay, so somewhere here. So it's going to be a little bit hard to do towards the right. But as you can see, if you follow the tangent lines, it seems like it's just going up almost vertically, and then it starts to shape like that. If you go towards the left, just following the lines again. And try not to draw it completely vertical, because if you remember, functions cannot have any vertical lines. But it seems we'd be doing something like this. Okay. And again, all I did is I'm following the tangent lines. Okay. So this is how you do problems like this. Again, this is not a 100% accurate picture, but it's very accurate. And again, probably when I do ask you to do this in the homework, I'll ask you to plot a solution like this, and then I'll ask you to actually find what the solution looks like in Mathematica, and you'll see how accurate these pictures are. Okay? So there are a couple more. Instead of going through this one, I'm just going to go through another example. Again, another direction field. This time it corresponds to dy dx equals e to the negative 0.01 x times y squared. Again, this is the right form. I don't know if I mentioned this before, but this is your function of x, y. Right? It's just an expression involving x, y, and constants. So let's just do a couple of them. Again, let's start with purple. So now we're looking for a solution that goes through the point x equals -6, y equals 0. So that seems to be somewhere here. Right? So that's the first thing you always do, right? Plot the point that you know, and then just follow the tangent lines. So if I follow the tangent line, it seems to be doing something like this. This almost looks like an logarithmic, not a logarithmic, a square root function, or a radical function. Okay. We could try something else. Let's see. Let's do C. So y of 0 is -4. So in this case, the x value or input is 0. The y value or output is -4. So go to x equals 0, y equals -4. So around here, and then just follow the tangent lines. And again, you can also do it towards the left. So it looks like it's doing something like that. And this first one, I can also follow it towards the left, right? Again, still just follow the tangent lines. And that's it. As simple as that. Okay. So as a summary, direction fields tell you a lot about the shape of your solutions without actually having to find them. And it's something that, as you saw, it's very easy to find or plot on Mathematica and also MATLAB and other software. You don't actually have to do it by hand.